show an example of what a language that isn't a regular language looks like? So we know, like,
well, a language that isn't a regular language.
Because I feel like you could have almost any set of strings, and then like, take a finite state machine that would recognize it.
Okay, we're actually out of time, but this course will not only show you one, it'll prove that particular languages are not regular. Okay, so that in fact is something we're going to do, and fairly quickly. Somebody asked to see a non-regular language. Is that person here who asked that? Okay. Well, in that case, I'm not going to go into it. We will actually, in not this lecture, but probably the next lecture, we'll see languages that are not regular and prove that they're not regular. So what I was going to do, if this person was here, was to show him one, and then he could go home and, or you can go home and fiddle with it and try to find a finite state machine for it and fail. And then that maybe build up your intuition. Actually, we're going to do that anyway. So try this one. The language is going to be the set of all strings, A to the N, B to the N, where, well, N is the same, it's the same N here, okay? So, you have, N can be anything, N can be N greater than or equal to 0, okay? So what this means is the following, like A, B is in a language because it's the same number of A's and B's. Okay. By the way, this symbol A, that's a number of the alphabet, raised to the N, that just means repeated N times. Okay, that's in the book, you might not have read that. So A repeated N times followed by B repeated N times. Okay, so that's a language, it's a set of strings. Here's another number of that language, double A, double B. Okay, that's repeated twice. ABA is not in the language, right? Okay, because that's certainly not A some number of times and then followed by B the same number of times because you have this extra A there. Or similarly AAB, that's not in the language because it's two A's followed by only a single B. All right, so this is a language, it's a set of strings, but I'm claiming that this is not a regular language. You can try to build a finite state machine for this, but you should fail. Okay, and in a couple of lectures, we'll actually prove that there's no finite state machine that can recognize this language. Okay, so sit with that if you have time, and that'll build up your intuition a little bit for when we get there. All right, but what I actually stopped with last time was the following claim. Let me remind you what the union of two regular languages is. So union of regular language A and regular language B, that's a set of strings, X, where X is contained in A, or X is contained in B. Okay, and you notice this or. So when you think of a union of two languages, you can think of a union is essentially talking about an or of two conditions. This is the condition for being, I was just saying it's an A, whatever it takes to be an A, that condition, or the condition of whatever it takes to be an B. I haven't told you what A and B are specifically, but those are two regular languages. Okay? And then the theorem that I stated, or the claim that I stated, is that if A and B are regular, then A union B is regular. Okay. And again, I'm using the fact that A is a set. It's a set of strings, and B is a set of strings, and so as sets, it makes sense to take their union. The A union B is a set of strings. Okay. So we're assuming that A is a regular language and B is a regular language, and we want to show that A union B is a regular language. We'll also, along the way, I don't know why you don't state this explicitly, but we'll show that A intersect B is regular also. So again, you have two different sets, and you can apply set operations to them. Okay, so but we'll do the proof first for A union B. And what I did last time was to show you a mistaken approach. Okay, we said, well, A is regular. So what does that mean that A is regular? What's the only thing we really know about a language if we know that it's regular? What I can say about it? Yeah, there's a deterministic finite state machine that recognizes it. Okay. Yeah, but what kind of, it gives you this misdirection. It first defines, it talks about machines accepting a language, and then it says, but don't do that. Don't say that word. It's talking about machines recognizing a language. Okay. So we know there's a deterministic finite state machine that recognizes A, and we know there's a deterministic finite state machine that recognizes B. And that's basically all we know about it right now. That's all we know about what it means to be a regular language. So let's say there's this M1 recognizes A, and M2 recognizes B. Okay, and these are two deterministic finite state machines. And then, because the only thing we know about what it means to be a regular language is that there's a deterministic finite state machine that recognizes it. In order to prove that A union B is regular, I have to come up with some deterministic finite state machine that recognizes A union B. All right. So the general idea is that we're going to somehow use these two finite state machines to build a finite state machine to recognize A union B. We want, I'll call it M3, that recognizes A union B. Okay? And last time, what I did, which I said was wrong, is to think about, well, you've got a machine M1 that recognizes A, and you've got the machine M2 that recognizes B, and this is an OR here. The union is really, the string X is in A or it's in B, so we'd like a machine, to build some kind of machine that would go through either of these, and then if either one of these accepts, it comes to a accept state or final state, then we would accept. But we don't have operations like that for determinate finite state machines where we can branch two ways, and then if either one of those succeeds, well, this is okay because we can just make these for final states anyhow. But we don't know how to branch two ways. We'll actually learn that today. But right now, we don't have that as an operation. This is a deterministic. We need to build a deterministic finite state machine, so branching like that isn't a possibility. Okay, so but the idea is that M3 should simulate M1 and M2 running in parallel. However, still parallel. So this idea of simulation is something that comes up over and over again in this kind of material, that with one class of machines, we can simulate another class of machines, or show that a certain language is, in this case A, B, and B, is recognized, when we have the components M1 and M2. Okay, so let me just show you, first of all, by example, I hope, how this works, and then I'll show you very formally how this works. Okay. Yeah, all right, so we're going to let A be a set of all binary strings with an even number of zeros. Even number of zeros. And B is going to be the set of binary strings with an odd number of ones. Okay. So let's just see an example in A. We need an even number of zeros, so it's 1, 0, 0, 1, 1, 0, 1, 0, 1. That has an even number of zeros, and so that's in A. Okay? And 1, 2, 3, 4, 5. Actually, this is also in B, because it's an odd number of ones. Okay? So this is a string which happens to be in both A and B. But let's say we had 1, 1, 0, 0. That's contained in A because it has an even number of zeros, but it doesn't have an odd number of ones. So that's in A, but it's not in B. Okay? So let me see what these two languages are. Now I want to show that, and then A and B are both regular. That's easy. Let's build a finite state machine for A. Okay, so M1, we even looked at one, I think, last time that does this. It's an even number of zeros. So there's the start state, which is also going to be the final state. There's a 1. It's terrible. 1. I'll give it a name, Q1. And then we go over to Q2 with a 0 back here, with a 0, and here with a 1. So this machine accepts the empty string, which has 0 zeros, so that's an even number of zeros. And then you can have any number of ones you like, but if you get a 0, you can then have as many ones as you like, but you have to get another 0 in order to get back to the final state. And then you can have more ones. And so this generates any binary string, but the only ones that it accepts are the ones that have an even number of zeros. Okay? So this is an easy finite state machine for M1. And then for M2, you want a machine that accepts binary strings that have an odd number of ones. Okay, and that's similarly easy to do. Here's a state Q1, that's a 0, 1, oh. The book typically uses the same notation for states in two different machines, and that's fine, but it gets a little bit confusing later on when we have to refer to both of them simultaneously, and the book does that by the position and the vector. I like to actually give different state names to different states in different machines, just for greater clarity. So these states will be called Q, and this will be P, and mathematically it doesn't matter at all, but I find it simpler to keep your list value. So this is P2. Okay, so this should be a machine that recognizes the binary strings that have an odd number of ones. So you can start with any number of zeros. You go over to here, this is the final state, that's 1, 1. You have more zeros. You go over there, and that's an even number of ones, and this is not an accept state, this is not a final state. So in order to get back to where there's a final state, you have to have a number 1, which makes it now an odd number of ones. So this is a machine that accepts the language B. Okay? But now we want a machine that recognizes any string that is either accepted by this one or accepted by that one. And as I was saying earlier, we can't just somehow put them in parallel. because we don't have an operation in deterministic finite-state machines that does any kind of parallel type branching. So we have to build a third machine that somehow is constructed from these two, but has a different idea. Now, how many people actually, this is the next page where I got to last time, and how many people have read that? I know some people have, the people who come and talk to me. Okay, all right, for those of you who haven't been, so again, the idea is to somehow simulate both of these. And the idea is that we're going to build a third finite state machine, and its set of states is going to be the Cartesian product of the set of states in M1 and M2. There's going to be all pairs of states, where the first state comes from M1 and the second state comes from M2. So the states in M3 are going to be Q1, P1, Q1, P2, Q2, P1, and Q2, P2. Okay? But this object here is a pair of states from M1 and M2. Right? But it's also, this object is also a single state in M3. And you have to have a think like a mathematician, as opposed to this, somebody off the street. This is just a funny name. Okay? It's a long, kind of awkward name, but it is just the name of now a single object, and there was a single state in M3, even though where we got that name from was from a pair of states from M1 and M2. Okay. And we'll simultaneously sometimes refer to this as a pair of states, and then you have to think, okay, pair of states from M1 and M2, or refer to this as a single state. In this case, we're obviously talking about M3. Okay. So this is the set of states, 4 states from in M3. And then what's the starting state of this machine we're trying to build? It's going to be that particular pair of states where they're both the starting state. So this is the starting state Q1, this is P1, so it's Q1, P1. Okay. That's the start state of M3. I'll get to the final state in a minute, but now I need to show you what the transition function is. So we're now talking about, again, M3, and so in order to distinguish it from the, now I guess what I better do is the transition function here was going to be called delta 1, transition function here is called delta 2, and this one, we'll just make it delta 3. Okay. So transition function. What's a transition function generally? It's a function on what? What are the arguments? Yeah.
The state of the language.
The state and the what?
It's like the binary language that will be like this.
Okay, and the term more generally is character in the alphabet. So this takes in a state, okay, and a state and a character. Okay, and it goes to a state. All right. Now, instead of the alphabet, all right, I didn't tell you what the alphabet for M3 is. It turns out the alphabet for M3 is the same as the alphabet for M1 and M2. They have the same alphabet. And so, to be completely formal and correct, you should say what the alphabet is here for M3 is the same as for A and B. Okay, it was sigma for, this is the alphabet for A union B. Okay. So this is what we want. We want a transition function which is over the states of M3 and the characters in the alphabet and go to the states in M3. And we're trying to simulate. Remember, we're trying to simulate what those two different machines would be doing, M1 and M2, whenever they see a particular string. So, again, working by example instead of by total formality, we look at each one of these states in M3 and we ask, for each particular character that would be processed in the input string, what do these two separate machines do, M1 or M2? So, for example, what does, we look at this state, Q1, P1, and it has these characters 0. Okay. So delta 3 of this, it's supposed to go to a state in Q3, which means it's a pair of states, one from M1 and one from M2. And it's supposed to be simulating what M1 and M2 would be doing. So you just ask yourself, well, what does M1 do when it sees Q1, when it's in state Q1, and it sees a 0? What does it do? Well, it goes from Q1 and sees a 0, it goes over to Q2. Okay? And what does machine M2 do if it's in state P1 and it sees a 0? Now it stays in P1. Okay? So this is the first transition rule. If you're in this state of M3 and you see a 0, you go to that state of M3. All right, let's just do another one. Well, before I do another one, let me ask, how many transition rules will there be? for machine M3. Not 8. Exactly, because we have 4 states, and we have an alphabet of size 2, and so it'll be